Welcome to our introductory lecture on the beam splitter experiment. This will serve as an introduction to the concept of quantum, and admittedly we'll be anticipating on a few of the topics that will be featured in Module 1. Okay, so here we're going to look at different interpretations of light, and we'll conclude by the quantum interpretation and how we can explain the beam splitter experiment from a quantum standpoint, and that will serve as sort of a motivation for studying those phenomena through the lenses of quantum. The first interpretation of light that we're going to present is the electromagnetic wave interpretation. What it means is light is considered a wave of the electrical field and magnetic field which satisfy the Maxwell equations that we listed here on the left-hand side of the slide. So these solutions in general case have this shape. So we're talking here about vectors, three-dimensional vectors, and the E for electrical field is the field that's going to be of interest to us, is the real part of the complex vector that has this vector here, E0, which is fixed, times this time-dependent oscillation here, okay? And we're going to be paying a lot of attention, of course, to this fixed E0 part, which is parametrized by theta here, this parameter theta, and delta x and delta y. Now let's see in the next slide some special solutions to the Maxwell equations. First, we have what we call linear polarization. Linear polarization means that we have here a difference between delta x and delta y, which is a multiple of pi. And what it means is that since we only take the real part, then we can factor by with an exponential 2i pi, and we end up with this kind of shape, and we call that linear polarization according to the angle theta. So if we're looking at, if we put x and y like this, then we have something that makes an angle theta, and the tip of the electrical field is going back and forth as oscillating on that plane, okay? Now, another very important solution to Maxwell's equation is when theta is pi over 4 and the difference of delta x and y is a multiple of pi over 2. And in this case, we have this shape, and once you take the real part, then the way it behaves is the tip of the electrical field performs this rotations, okay? So this is why we call that left-right circular polarization, okay? Now, let's see how we can detect light, okay? So we assume, especially like in here, we assume that we have managed to polarize light, okay? So how do we do this? Well, there are Polaroid filters that will allow you to take unpolarized light where you have also a superposition of all these special solutions, okay? So you have the linear polarizations in every possible directions, and your light is just a sum of all those potential solutions, okay? Now your filter will filter out everything but what is polarized linearly according to an angle theta. And then there is another tool that we need to talk about, is the Polaroid filter. The detector here is going to be measuring how much light we're getting, and what it does first of all is parameterized by its own angle with respect to the x-axis that we will call alpha in the rest of the lecture. Now the way it proceeds is that the result is that it gives you out an intensity which is given to you by the dot product of the vector E0 that we had in the input by this unit vector with angle alpha, okay, which is here basically, and this according to the direction alpha. So it will take as input light polarized linearly according to theta, and it spits out light polarized according to alpha, and there is a reduction of intensity, meaning that the norm of the vector E0 is going to be the projection of the original vector E0. So you get this cos alpha minus theta factor here. Now, the intensity is essentially proportional to the square of that value. It's in physical terms, it's the average norm of the Poynting vector, which is essentially ruled by this value here, okay? So the norm of E. And so the intensity coming in was E0 square, and the intensity coming out is E0 square times cos square alpha minus theta, which means that whenever alpha is not equal to theta, you lose intensity. You can go from alpha equals theta with no loss at all to alpha is theta plus or minus pi over 2, where you lose all the intensity and you detect nothing. You detect nothing in your detector. So now let's talk about that beam splitter experiment that I was mentioning in the introduction, and this is the motivation for introducing this here in this lecture, the quantum sort of perspective on light. Now, what we'll do is we'll repeat this sort of explanation of what happens when we take this particular beam splitter experiment with a wave interpretation of light, a particle interpretation of light, and then quantum. Now, what is this beam splitter experiment? Here, for the sake of this lecture, we're going to do something highly simplified. We assume that we have what is called a beam splitter. So it takes the incoming beam and somehow splits it, okay? And then one beam of light goes on a lower path, and one beam of light is propagating on a parallel path, which is an upper path. Okay, so we have the lower path, the upper path, and then there is the same beam splitter in reverse, which will recombine those beams of light. Okay, so let's see what happens when we explain light as an electromagnetic wave. We have here our source, which again we'll assume where we have polarized light according to, linearly polarized light according to an angle theta. Now it arrives at the beam splitter, okay, and now what you observe at the beam splitter is that 50% of the light, a certain percentage of the light goes on the lower path and another percentage of the light goes on the upper path. And it turns out that what it does is it splits, and everything that is polarized according to X goes on the upper path. So what it means is here we're looking at we're looking at a polarization that is according to X. So if this is the X-axis, this is our oscillation of polarization, and here, if this is our Y-axis, then our light oscillates around, the tip of the electrical field oscillates around according to the Y-axis, okay? And so if you put a detector here, you would observe a cos square fraction of the light. And if you were to put a detector here, you would observe a sine square fraction of our light, okay? So, and if you look at the electrical fields themselves, on the upper path, you have an E, you remember the E components that have this shape. So basically we lost here our component again around the, according to the Y-axis. And then on the lower path, you have this part where the E0 vector has lost its components according to the X-axis. And then after a symmetric operation, then everything gets recombined, and it's confirmed by the analyzer that observes the same intensity as it would have observed had it not gone through the beam splitter. Okay, so what it means is that's a very sort of satisfying explanation, because our beam splitter split both beams according to their polarizations. They took different paths, they were recombined, nothing was lost. So we're sort of happy so far. But here is what makes physicists unhappy. What makes physicists unhappy here is that at low intensity, light seems to behave like a particle, meaning that sometimes you observe something and sometimes you don't, as opposed to just having a lower fraction of the intensity. So it appears experimentally at a very low intensity that light is more of a particle. So let's see what happens if we redo all the previous experiments where light is explained as a particle. So first, what does it mean to be measured? So we assume that being polarized is a property of our photon, our particle of light, okay, which are called photons. And so the first thing we presented was the measurement. So what happens if those photons arrive one by one, not as a wave, but just as particles, and they hit the measurement apparatus, which is an analyzer with angle alpha, as we described before. Well, it turns out that we will see photons here only with probability cos square alpha minus theta. And what it means is it's compatible with the explanation that we have with wave. We had with the wave we had a fraction of the intensity, and here what we see is, in fact, when the photons arrive one by one, sometimes they're transmitted, sometimes they're not, and the probability of transmission corresponds to the fraction of the light that was observed. So far, we're sort of happy with that explanation, but here is when things are not going too well. Indeed. Now, if we want to explain the beam splitter experiment again by imagining that we have particles that arrive on the beam splitter, then the beam splitter will, will direct those photons either on the upper path or on the lower path, okay? And then here, the measurement apparatus will measure sometimes a photon and sometimes not. Now, what happens if a photon takes the lower path? Well, remember, on the lower path, things are polarized according to y. So that we've already observed, okay? So it's a y polarization here and an x polarization there. So we measure a photon. If we put a measurement apparatus parametrized for alpha equals pi over 2, which is we're trying to measure what's polarized according to the y-axis, then what we get here is cos square pi over 2 minus alpha. Okay, so, and that is sine square alpha, okay? And the probability of taking the lower path, we've already analyzed that experimentally to be sine square theta. Now, the probability of measuring the photon here with the measurement apparatus on the upper path, this, because the upper path comes with polarization 0, then it's cos square 0 minus alpha, okay, which is just cos square alpha. And then the probability of taking the upper path, which experimentally we observe to be cos square theta. And so the problem is that the probability here of measuring something is cos square alpha minus theta, which is not equal to this, okay? So here we have a conundrum. What it means is, according to classical probabilities, a photon, the probability of observing the photon at the end of the beam splitter experiment, as we described in this lecture, does not seem to follow the classical rules of particle behavior. Okay, so we're going to see now how it works when we have a different explanation of the polarization. And well, first let's see what happens with the polarization. So we assume that polarization is a degree of freedom of our photon and it has a state which is represented by a vector, a complex vector of 2 coordinates, okay? These 2 coordinates have the important property that the square of their norms have to sum up to 1, okay? And that means the sort of meaning to that is that the probability, so your polarization here can be found in 2 different possible measurements, could yield 2 different solutions. It could say that you're polarized according to the x-axis. We'll call that left-right, okay? And by convention, we'll map that to the first vector of the canonical base of C2. And the other possibility, which is your polarization on the lower path, is going to be according to the y-axis, which we'll denote as an up-down polarization, and we'll map this to the second vector by convention of the canonical basis, okay? So we have, in the scope of this experiment, we have 2 possible measurements for, 2 different possibilities for the polarization of your photon inside of the beams, between the 2 beam splitters. And so the probabilities of finding a photon in this state here is, the probability of a left-right polarization is going to be lambda squared, and the probability of an up-down polarization is going to be mu squared. And in general, we will map the E vector that has this generic form to this vector here. So you'll see that in the case of such a vector, the probability of the photon going through the beam splitter experiment and being found in a left-right, for example, polarization is going to be the cos square theta, okay? So that is sort of the formalism here. The takeaway is that we have a degree of freedom represented by a vector, and that vector encodes the probabilities of being in one of the 2 measurement outcomes, being, like I said, inside between those 2 beam splitters, it's only up, down, or left, right, and that state encodes the probabilities of finding your photon in this particular state. Now, here is what happens when we measure. So something funny happens in the sense that if we repeat that measurement experiment here, where polarized light is coming, linearly polarized according to theta, so we're talking about a state that has this shape here, cos theta left, right, plus sine theta up, down. And what happens when it goes through the measurement apparatus that is still parametrized by the angle alpha? Well, the measurement apparatus is going to actually, on top of giving you an answer, it will also change the state of your photon, map it from theta to alpha, where alpha is cos alpha left, right, plus sine alpha up, down, okay? And this happens with probability the inner product of those two vectors squared, where here, because we're anticipating a lot with respect to what is coming, I'm just giving you the inner product formula, okay, which is basically cos alpha minus theta. So we get the right probability, okay, the same as observing the particle, what we observed experimentally, that is the same here. We have cos square alpha minus theta probability of measuring your photon, and very importantly, moving its state from a polarization from the one here to the one here. Okay? Now, if we want to fully explain what is going on here, we have to account for a second degree of freedom, namely momentum. Okay, so polarization was sort of a first property of the photon that we're talking about, and now momentum is another one. And momentum is essentially encoding where the photon is going in at what at what intensity. So so then we have a state for the momentum. Okay. what does it mean? The beam splitter, so inside of the beam splitter, the momentum is quantized, which means that we're going to the lower path or we're going to the upper path, okay? And we'll map again by convention those two potential outcomes of a measurement, okay? So when we decide where is our photon, it's on one of these two paths. And then the state, the corresponding state, much like the polarization, is going to be a vector that is the sum of those two vectors with coefficients that satisfies that the sum of their square, the norm square, is going to be equal to 1, and the probability of finding your photon on each of those paths is going to be respectively lambda squared and mu squared, okay? So here, sort of the takeaway here is that while your photon in space can go anywhere, through the beam splitter experiment, the momentum of the photon becomes this value that is discretized, and it can be only found in two possible, it can only be measured in two possible values. You're on the lower path, on the upper path. And then we associate a state to that encodes, here again, the probability, so the coefficients of that vector, encode the probability of finding your photon in one of the two paths, okay? So that's our second degree of freedom. Now, those two degrees need to be combined, and so we can express the state as a vector in C4 that will encode all the four possibilities of a measurement of those 2 degrees of freedom, namely that we have our photon, the polarization of our photon that could be left-right, okay, or it could be up-down. And then for each of those polarization, you can find your photon in the upper path, lower path, or upper path, okay? So these are 4 vectors of a basis, and the state is going to be a linear combination of those 4 vectors with the following constraint, because here again, each coefficient is going to be, the norm square of each coefficient is going to tell you what the probability is to find the vector in a particular state. So for example, b squared, norm of b squared will be the probability here by convention, the probability of finding your photon on the upper path and in the left-right polarization. Now, what does the beam splitter experiment tell you? Well, the beam splitter has created the state here, which is, so if you just take the values of the electrical field, this is the state that's been created. And of course, though, we get that the probability of finding our photon on the upper path with left-right polarization is going to be cos squared theta. Okay, this part just basically disappears when we take the norms, the complex norms. And then the probability of finding it on the up-down polarization on the lower path is going to be sine squared theta. Okay, now what's interesting is, of course, because we've said that the beam splitter was only sending left-right on the upper path, we'd never find the probability of finding left-right on the lower path is 0. Okay. So what has happened here? First of all, our beam splitter, which is made of birefringent material, sort of sends photons with a different polarization on a different path. Okay, and physically it's explained by the fact that the refraction indices are different depending on the polarization. So you have, like, for example, glass at a 45-degree angle and an incoming photon, then the chances of so it will be reflected if it has a certain polarization, or it will go through if it has a different polarization, and this beam splitter is taking advantage of that. But by doing so, there are 2 very important things that we see here. First of all, the theory does not tell you where your particle is. The theory only tells you there's a state that has coefficients that encode the probabilities of finding your particle, on the upper path or the lower path. But that's not very satisfying. So one natural way to think of that would be, but it's not the right way to think of that, but it would be to say, well, quantum is just a incomplete theory, and in fact, there probably is a better theory to yet to be found, where an incoming particle, where we know everything about an incoming particle and about the beam splitter, and it will completely determine where that particle is going to go. Now, quantum theory tells you no, it's actually just you cannot know that. Now, Einstein didn't like it, though you may not like it, at least you have that in common with him. He said God doesn't play with dice, to which people answer, well, don't tell God what to do. So in here, we don't know where the particle is until we measure, okay? And before the measurement, then we just say the particle is either there or there. Once we measure, it will be exactly pinpoint, okay? But only when you measure. So that's the first thing that is very important to note. The other one is that the beam splitter itself has realized what we call entanglement of the 2 degrees of freedom, namely polarization and momentum. What does it mean? It means that after the beam splitter, as I said before, you cannot find your, for example, you cannot find your photon in a up-down polarization on the upper path, okay? So what does this mean? This means that the 2 degrees of freedom really aren't 2 degrees of freedom anymore. Once you fix the polarization, you also fix the momentum. So that means that those 2 degrees of freedom are entangled, and entanglement is going to be a really important part of quantum computation, quantum algorithms, because nothing really non-trivial is going to happen without entanglement, namely that if we want to compute with many bits of information, we will need some form of entanglement. So that's a very important demonstration of, practical demonstration of entanglement here, that those 2 degrees of freedom perfectly entangled in the sense that one entirely fixes the other, okay? So that's a very important state that has been created here. Now, let's just give you a quick overview of what's coming here. So in the first module. So first module, we'll start with a recap of vectors, and in particular we'll emphasize the Dirac notation, that the stuff with the brackets that I've been using throughout this lecture, and you might wonder why, what is this notation? So we're going to emphasize that. Then matrices, because everything is a linear operator, and so we will need to do a little bit of recap of linear operators and how they work, especially projections. Then qubits. So qubits are 2-level systems, so systems where you can measure things and the outcome is one of 2 values. For example, the quantized, the paths of the photons inside of the beam splitter experiment, which is upper or lower. So typical example of what a qubit could be. Now, tensor products, a very important mathematical notion, but also will be the essential tool to model the evolution of systems with multiple degrees of freedom. For example, the path and polarization of a photon, 2 degrees of freedom. Tensor product will tell you how to model, how to study this. And finally, unitary matrices. This will be the basis of our algorithms, because they model the action, they model the evolution. So the action of a unitary matrix on a state vector models the evolution of a closed system. So it's going to be very important, and that will be the end of module 1. So we have here a lot of linear algebra coming, and then in the subsequent modules we'll focus more on very important algorithms and their analysis. And here in this lecture we have anticipated a bit on some of the notions, but we will in module 1 take the time to recap and redo things rigorously. Thank you.